Close your eyes. Try to absorb all the positive things around you. If there is none, try to create one or two out of your own. Let's thank God for everything. Let us pray together. Our Father, who art in heaven, hallowed be thy name. Thy kingdom come, thy will be done on earth as it is in heaven. Give us this day our daily bread, and forgive us our trespasses, as we forgive those who trespass against us. And lead us not into temptation, but deliver us from all evil. Amen. Okay, so good morning once again. Last day we ended with plane polar coordinates, isn't it? Okay, we did plane polar coordinates, and I think you all are satisfied why we may need it, or not why, what benefit we can have if we need it, and uh, how we can connect back with the Cartesian system as far as the coordinates are concerned. That is, we can convert r and theta in terms of, I mean, we can write it in terms of x and y. Okay. Is anyone having any doubt in that part? Please ask. If you seek any clarification, else we'll move on to the next part today. Anyone is having any doubt? Please respond. If no, then we'll move. Take your time to recapitulate. Okay, no doubt from the boys. Girls, any doubt? Okay, I think that's a sign of optimism. That's silence. Anyways, so today let us begin the spherical polar coordinate system. Can anyone tell me when can we use this system? I told last day. Let me see if anyone remembers. When will this system be helpful? Anyone? Or what can we represent in this system? How is the point represented in this system? Don't feel shy. If you know the answer, tell. You may be correct or incorrect, nothing more than that. Don't wait that someone will say, then I will say, then no one will begin. Okay, then let me ask someone. Okay, Lachung, when will we? I'm asking Khushi that when should we use spherical polar coordinate system? Usually we are using Cartesian coordinate system. Okay, but why are we opting for this thing? I told last day. Why or when should we use this polar coordinate system? Yes, Lachung, tell me. Okay, where point is determined by 3 points of 3D. Okay, that is true, but that can also be done in your Cartesian system. Three dimension means you will have, in the simplest way to say, three axes or three directions. Okay, they may or may not be perpendicular to each other. Here, let us assume for the time being they are perpendicular. Okay, now tell me where the point lies. Lachung, can you tell me where the point lies in this situation? What is the surface on which the point is lying? I think all of you know the answer. I don't know why you are hesitant. Yes, Lachung, where is the point lying? It lies on what? It lies on a cylinder, it lies on a cube. It lies on a cuboid. Where does the point lie? Yeah, good. Sphere. Very simple. That is, here we are representing a point which lies on the surface of a sphere. Hence the name. Okay, very simple. I told that you all know the answer. You all are confused whether that is correct or not. Okay, then you should speak out. Like Nirupan said something, then I could understand that, yeah, he got halfway. Rest of the part needs to be uh, revised. Okay, so here the point, say a point P will be represented by three coordinates. Had this been an uh, three-dimensional Cartesian coordinate system, I would have written x, y, z. We did that while we were studying our first chapter. The Dasar is teaching you relativity. You will see there is x, y, z, and t. Okay, that's a four-dimensional space. However, here we won't need those 4D thing. 3D would be more than sufficient. So every point will have can be represented by three coordinates: r, theta, and phi. Last year we got an idea of what r and theta are in plane polar coordinates. R is more or less the same thing, but theta and phi are a bit different. What are they? So in order to help you understand, I made this thing. Okay, uh, you can easily make it at home. We all have broomsticks at home. Those sticks you can cut and you can paste together so that it looks like three mutual axes. Okay, say x, y, z. Okay, you can make it at home. I'd recommend you all can have one, because it's often very difficult to understand 3D pictures which we'll draw. Okay, and if you have any doubt, you can take reference of this one while you're studying. So I'll draw this system. So you can see it's a three-dimensional picture. Okay, if I draw it like this, what about this thing? How can I draw this thing? What we draw? We draw a line which is making equal angle from both the lines. That is, this picture we can draw like this. Got it? What I made? This axis is this one. That is, this one is perpendicular to the plane of the paper. Uh, you can define any axis as x, y, z. It's up to you. I told you there's no hard and fast rule that this has to be x, this has to be y always. If you're plotting those graph in equation thing, that's a different issue. Else, you can draw it. You can name any axis as x, y, z. I'm following A.B. Gupta's book. You people Many of you have that book, so I am following the notation used in that book. So in that book, these are the three axes. Okay, say y, z, x. Is it clear, everyone? Now I have a point called say P. What I said the coordinates of the point would be now r, theta, phi. Fine. So this is the axis. Okay. I have a point here. So the coordinate of the point is r, theta, phi. Can you understand the picture? This thing? Are you able to visualize that this thing is this thing only? Please respond yes or no. Fine. So what is r? Simply the line that you will get if you join the point P with the origin. You can see, yeah, the problem with this thing is that that's reality. It's not so uh, poetic always. Okay, it's pathetic rather most of the time. So origin should be a point. So when you're sticking everything, definitely it won't be a point. It would be clumsy. If you have that super glue kind of thing, then yeah, you can take it out. So we are thinking that somewhere here is the origin. There's a fixed point here, and if I join that point with the point P, P say somewhere here, then this would be R. So this is my R vector. More or less same as that in plane polar coordinates. It's same in fact. Now suppose I have drawn R. So this is my, if I can insert it somewhere. Yeah. So this thing is R. Okay. So this is R. So you can see R is making an angle with the Z axis, isn't it? Yeah. This angle. Can you see R is making an angle with the Z axis? You can see from all angle, if you visualize from different portion, you will see that there is an angle between R and the Z axis. Clear? This angle is this one, theta. So R is what? What does the coordinate R mean? It is the radial distance or radius vector also sometimes we call it. So also called the radius vector. It is the distance of P from O. What is theta? Theta is the angle which it makes with the vertical axis. It's not necessary. I am again telling you, if you call this one X, this one Y, this one Z, then theta is the angle made by R on the with the point with the vertical axis. Okay, so it is the angle made by R vector. You can call it a vector as well. Vector with the vertical axis, which is in our case the Z axis. Okay, so now you may be thinking that, sir, then it looks kind of this, a two-dimensional thing. Okay, why? We have R, we have theta. And how is this thing going to be 3D? It is going to be 3D if there is another angle. Which angle? This angle. Okay, the angle which it makes with the, or the angle made by R with the plane, this plane. Which plane? ZX plane. Okay, this angle. So This is r, this is theta, this angle is phi. So you can see you have three things now. How far it is from the origin, at what angle it is with respect to the vertical axis, and what angle it is making with this plane. Do you understand the three things? So what is phi actually? Phi is, sorry, this thing has a name. It's called the co-latitude. However, these things we won't be calling very frequently. Co-latitude, and uh, phi is the angle made by, if you think in terms of plane, it would be better to understand, made by the plane containing r vector with the zx plane. That is, in our case, this is the zx plane. Okay, and its name is the azimuthal angle. Pictorially, we can say that angle phi is this angle. I don't think the dots are prominent. The broken lines are prominent. Now it should be. Got it. These are the broken lines, means they don't exist in reality. For our understanding, we are drawing them. So you can see zx is a plane. What do you mean by a plane? Z, y, x. This is a plane. If you put a piece of paper here, if you just fill it with a page, okay, say this. So this is your zx plane. Okay, and what is your r? R is this distance, isn't it? So you may think that r is also on a plane. Say r is in this plane. Okay, say this is just a moment, let me use another page so that it will be easier for you to understand. Say this is r. Okay, this is r vector. It is on a plane. This page is the plane, and see, now this is the plane containing r. Can you visualize that the vector lies on a plane which is movable, and the angle which this plane makes with this plane, that is angle made by the plane which contains r with the plane zx, is your azimuthal angle. Is it clear, or shall I repeat? Please tell.
So repeat.
Which part? And these planes.
Yes, sir.
Okay, just hold on. So this is r vector. I don't think there is any doubt. Now I am telling that you have to visualize that this r vector is also on a, it lies on a plane. What is plane? Simply something like this. If this is the r vector, the surface on which you have drawn it. Suppose this one. Let me cut this thing. Okay, so this is the plane on which this r vector lies. Okay, you can make it a larger plane as well. So now I can say that r vector lies on a plane. Did you get this thing? R vector lies on a plane, which makes a certain angle like this. Did you understand this thing, everyone?
Yes, sir.
Now, how to represent this angle? You can see the plane is not like this. It's not in the YZ plane or not on the ZX plane. It is making an, you can see, yeah, see, there is a angle. How to define this angle? For that, we have to define a plane here, because angle between the two planes, that is this angle. So what I will do for that, I'll again cut a piece of paper and y z y z x. So this is my xz plane. This one. Let me stick it. Okay, then it will be even more clear. So you can see, if you want to understand physics, it's really interesting, provided if you are willing to work hard and if you are interested in this art and craft things. I am very much interested in those things, so I am trying to make a plane. Okay, yeah. So this is my ZX plane. Clear? Z axis, x axis, and this is the ZX plane. Is it clear now? What is the ZX plane?
Yes, sir.
That is this plane. And now I am telling this plane is the plane containing R. So now I am telling that, yeah, this angle, the angle made by this plane which contains R with the ZX plane, that is phi. Okay, this angle which this plane makes with this plane. Got it? That is phi. Simply put, this angle. And if you want to visualize it with only the R vector, it would be a bit difficult. You have to draw perpendiculars here. Okay, then you have to join this line, then you have to find this angle, and it is better to visualize in terms of planes. Understood? See, this plane is making an angle with this plane, that angle is phi. Is everyone clear with this? Please respond.
Yes, sir.
Okay, so that angle is phi. So you can see how two angles and one a distance, it is distance at the end of the day, they can define completely the position of any point on a spherical surface. Now it is important to understand the unit vectors, the directions. That is, what does unit vector tell us? They not only tell us that this is x-axis, j cap is for y-axis, k cap is for z-axis, but more importantly, they also tell us that in which direction, if you go, that axis is positive or negative. That is, j cap will point towards this direction and minus j cap will point towards the opposite direction. Hmm. But here the unit vectors tell you that in along which direction these r theta phi are increasing, or in which direction you should take them so that it is positive. That is, you see, if you move along this direction, I'll call it r cap, then this is a direction of increasing r, isn't it? Along this direction, r is increasing. And is the what should I say? The convention here that the angle is measured from z-axis to away from it. Okay, you can see usually what we do in polar system, what we did, we call this x, we call this x, we call this y, p, we call this r, we call this angle theta, isn't it? But here this angle is theta. So if your radius vector moves downwards, okay, then your theta will increase, isn't it? Theta is the angle made with r, and this made by r with this axis. So if you go along this direction, you can see the angle is increasing, isn't it? See, the angle is 0. It's increasing, increasing, increasing. It is now 90°. So what is the direction of increasing theta? Along which direction theta will increase? This direction. Which direction? This one. That is, theta will increase along this direction. See if you understood or not this thing. I think I should decrease the level zoom. Acha. Did you understand? Please tell these directions. Fine. So, and obviously, the more you move away from this plane, this more you move away from this plane, your phi will increase, isn't it? What is phi? This angle made by r, or the plane containing r, and this plane. So 0°, go on increasing, increasing, 180°. So the direction of increase of phi is along a direction which we can't draw perfectly in 2 dimension. Okay, so we draw it like somewhere here. That is phi cap. Likewise, we can't draw it like this, so we are drawing it like this, like that only. This phi is along a direction which we can't draw in the paper, but we can understand. So these are the directions of increase in theta, phi, and r. Please tell me if you couldn't understand anything, or if you have any doubt in any place, please tell me. This will take some time, okay? I won't just sprint all the way. Is it fine? Okay. So now the important thing, we have been introduced with some new things, but for our better comprehension, we should also know how we can connect these new things with the old things. That is, what is the relation between the Cartesian and spherical polar coordinates. That's very, very important. When we know something new, in order to apply it, we have to connect it with our past experiences, our past knowledge, isn't it? If everything is totally new, we would mess up everything. That is simply, I am asking you that if the same point P in Cartesian system has coordinates x, y, z, and the same point in polar spherical polar system has r, theta, phi, then how are these things connected with each other, x, y, z, and r, theta, phi? For that, we will require uh, abundant use of trigonometry. Don't panic. And you have to have the power of visualizing. In physics, you have understood relativity when you have studied. Not everything around you can be used as an analogy to understand everything, isn't it? Where will you find in your place, anywhere you go, where will you find that someone is running and he's or she is getting heavier? But relativity says that if you move with the, I mean, if you don't have the idea that the speed of light is absurdly too much compared to the normal uh, velocities, range of velocity, then you won't be able to understand it. Where do you see length is getting contracted? How can you visualize fourth dimension? How can you inculcate that concept of the time is not, I mean, absolute, isn't it? We put time absolute only, then we, as if that is the center and surrounding it, we make circles. So there are many things you need to visualize, like the thought experiment. And did you study the twin paradox experiment? Do you know that the twin paradox experiment in relativity, a thought experiment? Yeah. So where will you get this that thing to be done, isn't it? So those are called thought experiments. That uh, the biggest laboratory, uh, Rutherford. I think you know his name, the one who uh, explained the structure of atom. He told his research scholars, that is the people who used to do research under him. He never used to keep them too much in the laboratory. After 6 hours or 5 hours every day, he used to just shove them away, and he used to say that just go home, relax, and think everything, because the biggest laboratory is our brain, not the lab that we have outside. The thought experiments are the experiment that you do in that laboratory. You have to close your eyes, you have to visualize. And Einstein, Tesla, these people were expert in doing that. Okay, so that imagination power, a constructive imagination, a disciplined imagination, it's not that you're imagining randomly anything is coming to your mind. Okay, that won't fit the frame of, that won't fit with reality. Okay, you have to be imaginative, you have to be disciplined, and you have to visualize everything inside you. And that visualization power will be very helpful, because many times we will encounter three-dimensional things that we have to draw in 2D. Don't worry, PowerPoint has come. You will say that, sir, today we have PowerPoint, we have those video. That's true. You can go to YouTube, you can search anything, but still you have to develop that visualization skill. That this picture is 2D, you have to close your eyes and you have to imagine, yes, this is 3D, this is along this direction, this phi is along this direction. And in solid state physics, that thing would be very, very helpful. That's my personal experience. When you will see crystal structure, lattice structures being drawn on the paper, and there are many things, atomic packing fraction, then nearest neighbor. There are many things that you will easily understand. You will understand way before others. Okay, fine. So what we will be doing for finding this thing, we have to draw perpendiculars on this axis and from here on this axis as well. Say it is R, this point is Q, this point is S. That's true, it doesn't look like 90-degree. Again, remember, it's a three-dimensional picture. Okay. Say this point is Q. This Q is actually here. From here, I'm drawing this thing, I'm drawing this thing. Got it? So can you understand that OP, P has become significantly small in my picture? Yeah. So can you imagine that OP has a projection on the XY plane, that is OQ? Can you understand? Projection, I think you all know this kind of thing only. Say F2 axis, say it is the X direction, is the Y direction. I have a vector A making an angle theta. So the projection of this vector here is what? A cos theta. That's called the projection. So can you understand that OQ is the projection of OP on this plane? Visualize, try to visualize it. No problem if you can't visualize. We have this homemade mm, coordinate system. We can utilize that as well. Okay, I have removed that YZ plane. So this is R. Okay. See from all angles. I need to increase the altitude. Yeah. Now it looks better. Yeah. So this is R. I hope you are all okay with R. Now I am telling that this R has a projection on this plane. How to draw projection? You have to drop a perpendicular from this tip. Where will that perpendicular land? It would land where? Here. It would land here. On the which plane? XY plane. I think I should change the angle of my camera. Just hold on. Yeah. So can you see it? Y, y-axis, z-axis, x-axis. Okay. This is R. Is it fine, everyone? Please tell.
Yes, sir.
So what I will do from this tip, I will drop a perpendicular where? On the plane of the paper. That is my XY plane. That is, say, I need another small portion for that. This will be very careful while dealing with these broomsticks, okay? If they get stuck anywhere, see a doctor immediately if that bleeds, okay? Or if the splinters stuck inside. They're very dangerous. Yeah. So see what I have done? I have dropped a perpendicular. I will require an assistant. Once uh, the college begins, we'll do this thing, and I think our CRs, Priya and Shubha, you can assist me. Did you understand? A perpendicular is being dropped. Clear, everyone? Is it okay, everyone? Yeah. Now, from this base of the perpendicular to that origin, if you join, you'll get what? You would get a straight line on this plane. That straight line is a projection of R. That is, I am drawing a straight line from. I'll use another page. This page will look dirty. From here to here, say this. Okay. So this straight line is the projection of R on this axis. Okay, got it. So that is what the projection thing is. Clear, everyone? Please tell if you are not clear. Okay, good. So I can say the projection of OP on, not on, projection happens in, on also can have, no problem, in the XY plane is OQ. Now, if you understand that thing, then you will also understand, not apparently, but it will take some time to realize that OQ is nothing but it is R sine theta. You say, sir, where come theta is coming? There you have drawn phi, you have written phi. Theta is coming due to the fact that this line and this line, these two are parallel. Both are perpendicular to the plane of the paper. That is, this line is this one, and this line is this 90 degree. This one. So both the things are parallel. This and this is parallel. And R is what? R is acting as as if it is a transversal like this. I required more than 2 hands for this. Okay, see, parallel lines and a transversal. If this angle is theta, then this angle will also be theta. Got it? That famous theorem. And the outcomes, then this angle and this angle would be called alternate angle. This angle and this angle would be equal. So this angle here is also theta. So if this is theta, this would also be theta. That won't be very clearly visible here, but if you take this reference, it would be clear. Okay, and this is actually 90 degree. Why? This one. It is what? It is the projection, isn't it? The projection is on this paper. Here is our projection. Projection is on this paper. And this is your R vector, and this is your perpendicular. So you can see it's a right angle triangle. Isn't it? It's a right angle triangle. Is it clear, everyone? How it is a right angle triangle? So the projection is the perpendicular of the triangle. The projection is the perpendicular of the triangle, and we know that the perpendicular component is the sine component. Okay. These things actually when we were taught, I was in 2000. I was a first year student in 2011. Yeah. So nearly 10 years, 1 decade ago, we first studied these things, and weren't given this demonstration. Teacher used to rely completely on our imagination, and needless to say, not everyone is imaginative. And it took me nearly two or more than that to actually realize that yeah, this is sine theta, this angle is this is actually 90-degree, and I don't want to people to waste 2 years for doing that. So that's why I'm trying to use tools, this teaching tools, learning aids for this thing. Okay. This may look childish, okay, as if you are a school students, you are in the play group. I'm just showing you an apple and telling this is a for this is apple, but you will never forget what apple is, isn't it? Because you studied it that way. And these things are, if you want to lead the life of a physicist, these things are more important than apples. Okay, so you have to be very, very careful and clear with these things. Okay, so quickly I'll just try to wrap up that the same thing r theta phi in the coordinate called Cartesian coordinate system, it is also xyz, isn't it? So we got the projection thing. So what is x? X is this distance. How much? Sorry, this distance, isn't it? How much it is in front? That is this distance x. How much it is in front? What is that? It is over. What is y? How much it is towards the left? That is this thing. How much it is towards the left? This much is y. So y is equal to what? Pictorially, y is equal to OS. And z is very simple. How much it is? How above it is, this thing. And if I draw perpendicular, these two are perpendicular, so it would be parallel. So I can say that z is also equal to pq. Please tell me if you understood this or not. Clear, everyone? I think you are not getting to see the interface. Yeah. Fine. So OR is what? Very simple. OR is again you can see here is a right angle. You have understood. It's a 3D picture, so it's not looking prominent. So it's the perpendicular of the triangle. It is the base of the right angle triangle. OQ is the hypotenuse. So OR is what? Base, and base can always be written as cos theta, that is this angle, into hypotenuse. Clear? Take that out. This is actually equal to it's like this R Q O. So what would be and this angle is phi. So what would be over projection? That is OQ cos phi. The similar logic, and if you can visualize that this is perpendicular, so this is also 90-degree, then these two angles would be equal, alternate angles. Then OS is what? OS is the perpendicular of this angle. What is this angle now? OS Q. This angle is phi. So what is OS? The perpendicular of the triangle. And perpendicular is equal to hypotenuse into sine phi. And what is PQ? Very simple. PQ is nothing but this thing. Again, here it is a right angle triangle. You can see how clumsy it is becoming. 90-degree base. So PQ is nothing but PQ is simply R cos theta. And OQ is again r sin theta. So if we put the values, we would get, who is texting me now? Phone is getting right jumped. Please. Sin theta cos phi. OQ means r sin theta. And we have sin phi. So see, that is how x, y, z are related with r theta phi. So that is the relation. I don't know whether the relationship is a heavy one, but it's a very important one. And it's your homework. Try to find, try to find what is this thing equal to, and what are the values of theta and phi. Okay, so this would be your homework. Clear, everyone? Put your questions if you have any. Is it okay? If there is no doubt, you may leave for your next class. It will begin in less than a minute.
Thank
Okay,
you,
thank
sir.
you. Thank you, everyone. Take care. Yeah, everyone has left.